Alrighty. So today, why was e to the x so cool? Not just was, I guess it's not past tense. Let's change that right now. That needs to be is. It is present text. It is clearly is cool. Why is, yeah, yeah. That's even a single line, way better. Why is e to the x so cool? Because it really is. If you don't think it's super cool, that's fine. But after today, you'll understand why it is so cool. So today we're learning to find the derivatives and the integrals of exponentials. We'll be successful when we can find out why Mr. Last loves e to the x so much. So much. Oh my gosh. Like, I really, really enjoy it there, folks. So, does natural log of x have an inverse? Yes. Whether or not it was a function is not up for concern. But the thing is, there's natural log. Does it have an inverse function? Yes. Because if you look at this, based on what we talked about yesterday, natural log is monotonic over this interval because the derivative of natural log is 1 over x. And on the interval of 0 to infinity, the domain, oh, that's right, it's positive the entire time. Thus, its inverse is also a function. Oh, let's put that in there. That's kind of a helpful thing to put in there. Yeah, I'm totally going to edit this as we're going. Okay, is positive on the main natural log of x, thus making natural log of x monotonic. Hey, look at that. Already making some improvements. Oh, all right, well, that's fine. I'll putz with the animation later. But because the derivative of natural log of x is positive on the domain of natural log, thus making natural log monotonic. And because it's monotonic, its inverse is a function on this interval. So we're defining e to the x to be the inverse of natural log of x. Again, in pre-calc, we defined it differently. A lot of things we define differently in pre-calc. Pretty much every other class except calculus defines them in these particular ways. Why do we do it? Because of the ease of differentiating and integrating is why. So we're defining e to the x to be the inverse of natural log of x. So if f of x equals natural log of x, then f inverse of x equals e to the x. We can also state it like the following. Y equals e to the x if and only if the natural log of y is equal to x, which we can see by exponentiating both sides or with a base of e or taking a log of both sides, a natural log of both sides, boom. So it depends on your properties and kind of where you're coming in from. Now we're saying this is true. Remember, I mentioned this a couple times, but the IFF is if and only if. It means that if y equals e to the x, then natural log of y equals x is true, but also the reverse is true. If natural log of y equals x, then y equals e to the x. So if you can say if-then statements both ways, you can just put if and only if in the middle. So fun logical facts for you in the morning. So here are two rules for the natural exponential function, is what sometimes we call e to the x. But when I hear natural exponential function and e to the x, I'm going to pretty much always say e to the x because it just is shorter and more efficient. The reason we call it natural exponential function is because ln is natural log So its inverse is natural exponential. Okay. But there's some other rules for exponential functions in the book. You should definitely check them out. But here's the idea. Here's the two ideas that I want you to get out of this. The derivative of e to the x is e to the x. Like, that's it. That's honestly why I like it so much, because I think it's so freaking cool that it's its own derivative. And for that matter, it's its own antiderivative too. This first one is the original. The second one was me trying to be clever and it didn't work out as well, but whatever. But anyways, the antiderivative of e to the x is e to the x plus c. You have to remember that plus c. Make sure you do that. Ask me at the end of class and I'll talk about it then. Okay, so to finish up this, why is e to the x its own derivative? Like, I said it is, but why? Like, just because I showed you this doesn't mean it is a hard and fast rule. Like, just because someone tells you something doesn't mean it's true. Like, I've experienced that for 4 years. So let's keep looking at something and let me show you why it's true, because we should listen to science and facts and math in this case. All right, so why is e to the x its own derivative? Oh, that's right, I should have changed the way that x. So what I'm going to do is I'm going to try to take the derivative of y equals e to the, here, let me grab my pointer. Y equals e to the x. I'm going to take that. But again, I don't know where to even start with that. So what we're going to do is do logarithmic differentiation. So I'm going to take the natural log of both sides to get this. Then we're going to, because one of the properties in logarithms is I can take the exponent and bring it out front, right? That's the power property of logarithms. All right. So it's still that. Now, fun fact, again, we defined natural log of e to be equal to 1. So I just get natural log of y equals x. Hey, I know the derivative of x. I know the derivative of natural log of y. Let's take the derivative of both sides, see what we get. Which when we do that, again, this side is 1 over y times dy dx, because we're taking the derivative with respect to x. But the derivative of x with respect to x is just 1. Which means we can multiply by y to get dy dx. But y, based up right from here, is e to the x. I don't know about you, but every time I go through that, I'm just always like shocked. And I'm like, that's so freaking cool. Like, oh my gosh. Like looking at how that all plays out, it doesn't seem fair how cool it is. Like, it's so freaking cool. Oh my gosh, I like it so much. But that's why e to the x is its own derivative. It's partially because of its relationship with natural log is y. All right. So, and for that matter, this can be extended to be y, the antiderivative e to the x is e to the x. Okay. That's it. Like there isn't much to this section. There's a lot of just looking at it and practicing a bunch of different things and trying and see how you do. So there is the practice. Again, there's literally 9 problems. There's not really that much. I have some extra examples you can look at on the next page, but they are possibly kind of ridiculous examples. I just kind of made stuff up randomly and that's what I got. But that's really all there is to 5.4. It's just a matter of taking some time to work on 5.3 and 5.4 and getting those done. If you happen to get done with these 9 and submit them, you can start reading through 5.5. Again, with 5.4, make sure you read the section. I didn't say that in there. I'm also going to say read the section. Yeah, and especially in this chapter 5, like seeing how these college professors write books a little bit differently, because they write it to show you how smart they are, and not necessarily how smart you are or how intelligent you are. It's important to take some time and read those things. So there's that.